Lesson 9.2, Proofs Using Coordinate Geometry. This lesson is very confusing for a lot of kids. So keep in mind, this is a conceptual lesson to make sure you understand the concepts and understand the big ideas of proving things on a coordinate plane. So it starts out actually having you critique other students' work, which is a really good question. Dakota and Jung are trying to show that the triangle is a right triangle. So Dakota solves it this way. Finding the slope of each of the two sides, and the slope of when they are multiplied together give you -1. So would that prove that it's a right triangle? That's Dakota's. Jung takes the distances or lengths of each side, takes a squared plus b squared equals c squared, and says, oh yeah, this does work. So that's a right triangle. So you have to determine, is Dakota right? Is Jung right? Are they both right? These two versions of the same problem give you a hint into how this whole lesson is going to be. There is not going to be one perfect way to solve each of these problems. So keep that in mind. And if you look at the solutions or you're checking answers, don't get too nervous if your answers and the way the book solves it or the process is different. It's okay. All right, example 1, plan a coordinate proof. So think about proofs where something is given and you have to prove something step by step. It's the same concept, but with coordinate geometry, you're actually going to use the math. You're going to find the distances, you're going to find the lengths, you're going to find the midpoints, and you're going to determine, say, hey, look, these distances are the same, therefore things are congruent. So your math is going to be like your justification instead of like straight rules. So how can you use coordinate geometry to prove geometric relationships using the trapezoid mid-segment theorem? So hopefully you remember what that is, but let's go through this solution step by step. So first of all, when you do this, use the coordinate system or the graph in the easiest way possible. Generally, starting at the origin, 0, 0, is helpful. When you go over to other points, use the x-axis, use that y-axis to make your coordinates a little bit easier. Like if I go over d amount, the coordinate would just be d0 because it hasn't gone anywhere vertically. And then this point C, it goes over C and up B. This one over A and up B. So use just like simple A, B, C, D. If you use actual coordinates like 2, 4, 6, actual numerical values, that doesn't prove it for all. That's just an example. And so that's why when you do these proofs, it makes it a little bit harder because it's the concept. It's using all those variables instead of actual numbers. Where in the last lesson, we used actual numbers for actual examples. Okay, so first, draw the picture, give the visual. And so you need to restate the theorem you're trying to solve. So the theorem kind of says this they reworded it a little bit, but it says the mid-segment of a trapezoid is parallel to each base and its length is 1/2 the sum of the length. So you have to prove that the bases are parallel to the mid-segment. So keep that in mind. You'd have to show that the two bases are parallel and the mid-segment is parallel to those bases. And then you're going to have to show mathematically that the length of the mid-segment is 1/2 the sum of the two. So let's look at this. To restate, you are like literally what I just said. You need to show that the slope of EF is the same as the slope as AD and is the same as BC. So you need to mathematically show that. And then you also need to say, if I added these together and divided by 2, that would be the average, and that would give me the mid-segment. So let's look at it. It says make a plan. Well, to make a plan, you are going to have to, well, how do I find the slope of these? Rise over run. Find the slope of EF. So I go to EF. Well, it doesn't rise at all. So there's no rise and a run. So the slope is 0. Hey, look, there's no rise. So 0 slope, no rise. So 0 slope. So you're like, oh, okay, I would show that each of those slopes equals 0. Therefore, they're all the same. And so I have just shown this, that the slopes are the same. Now I just need to show that when I add them up. So when you do that, AD, that length is literally D. From B to point C, oh, pause. The next thing you would have to show is that EF, that midsegment, is the same distance as adding the bases together and dividing by 2. So this is a tricky one because this is having you make the visual. Plan a proof that shows the diagonals of a square are congruent and perpendicular. So kind of restate it. I am showing a square. So, and it gives you a little picture here, like a ability to draw a picture, I should say. So you can draw. Mine are terrible. Keep that in mind. Hopefully you can draw a little bit better squares than I can. And when you draw this square, you can draw in the diagonals. I need to show that these diagonals are not only congruent, but that they are perpendicular. So to be able to do that, I need to make the plan. Okay, the diagonals. How would I show that 2 segments are congruent? Find the distance. Find the length of those 2. And then how do I show that 2 segments are perpendicular? Find the slope of those 2 and make sure when you multiply them, they equal -1, those slopes, or that the slopes are opposite reciprocals. So let's look back here at this answer. And it says, draw the square, start at the origin, which I did, give the points. And remember, these points might not be the same as yours. Just give them variables and make them as simple as possible. And then literally find the distance. And because these coordinates are like variables instead of numerical values, you might want to use the distance formula. And remember, that distance formula is taking the square root of the x values, or the difference of the x values squared, plus the difference of the y values squared. So that's all one big formula. That's the distance formula, if that helps. And then to find the slopes, rise over run. So if I look from this point, B, C, that rise, I look at the y values, it's just a, because a minus 0 is just a. And then I look at the x values, a minus 0, a minus 0 is just a. So I have a over a. Oh, my slope is 1 right here. This slope is 1. M equals a over a, which is just 1. And then if I do the other side, where I find the rise, the difference, that's a. This difference, a, that's a as well. So rise over run. So my slope here is a over a, but it's negative. And when I reduce that, that's -1. When I multiply these 2 together, I do get -1. So find the slope, use the variables, but keep in mind, mathematically, you can still do the math, even though they're variables. So set them up. You're going to have things like a over a or b or whatever the variable is, and just set them up so that you can show that, hey, look, the slopes are opposite reciprocals. This problem, example 2, asks you to write a proof for the trapezoid midsegment theorem, kind of like what we were just doing, but this time it says given, and so it looks more like a proof. Given this trapezoid with these midpoints, prove that these are parallel and that EF equals that. Well, this is what we just did, so make a plan. To show that these are parallel, I literally have to find the slope of this segment, segment EF, and this segment down here, AD. So I need to find all 3 slopes. If I can find all 3 slopes and show that they are the same, like rise over run, then I have proven this first part. Then I go to EF, and I need to show that EF is the same as AD, which is down here, this length, and this length added together divided by 2. So this step-by-step solution does it. It says, hey, look, the slopes are the same. And I need to do this. That's my goal. So I need to prove that. So it says, actually use the midpoint formula to find the coordinates of E and F. Because on this problem, if I go up here, it doesn't give you the coordinates. So you kind of need those first. So get those coordinates. Remember, midpoint. Don't confuse that with like distance formula. The midpoint, you literally should end up with a point. So once you get the midpoint for each of those, then you find the slopes of each of those, and you can use the slope, rise over run, or you can use the slope formula if that helps. Let me write that down for you. the slope of any one of these segments, you can have y2 minus y1 over x2 minus x1. So this is the slope formula, and that might be a little bit more helpful than counting rise over run because you're counting and it's a variable. So keep that in mind. Step 3. Determine each of these, like the actual length of those, and it shows you how to do that. And you're literally finding the difference or distance between, luckily they're all horizontal, so that makes it a little bit easier for you. And once you have that, then you're going to take these distances and use some algebra to actually add them together and divide by 2. So you can do this. It just seems very scary because it's conceptual and it's all these variables, but I know you can do it using the formulas that you have. And to be honest, if you get stuck or are confused where to start, I would start using these exact same coordinates if you're talking about a trapezoid. Okay, and if you're using like a square or something like we did in another problem, use the exact same coordinates they use because those work and you know that you don't have to like make up your coordinates, if that helps. Use coordinate geometry to prove that the diagonals of a rectangle are congruent. So let's start kind of more basic. Let's start visually with this. I'm going to go over, and you can make it look, well, more like a rectangle than I can because hopefully you can draw better than I can. So I am going to say this point is 0, 0. Now, I don't know what the book says or what this computer-generated thing says. I'm just going to take this point and say A0 because I went over A and I didn't go up at all. And so this point up here would be over A, but up some amount. So I'm going to say A, B. I don't know. This coordinate, I didn't go over it all, but I did go up B amount. I don't know what that means. So just some amount. And I'm just putting these on here, even though I don't know what's in the actual solution. So it says, use the coordinate geometry to prove that the diagonals of a rectangle are congruent. So I'm talking diagonals. I'm going to draw in those diagonals right away so I can say, okay, I need to prove that this segment is exactly the same as this segment. So that means distance formula. And again, I wouldn't use Pythagorean theorem because it's hard to use Pythagorean theorem with like A's and B's and different variables. So I'm going to use the distance formula. Thinking about the distance, I'm going to use the x's squared, the difference of the x's, plus the difference of the y's squared. And look, x, y, x, y. Each of these has an x and y value. So to find the distance right here, we'll do this side to side diagonal. I'm trying to make it thicker. I'm going to take that and say, okay, my distance is, well, my first x value, I'll use this for first point, is 0 minus a squared. My y values are 0 minus b squared. So when I look at this, I'm going to end up with a negative a squared plus a negative b squared. Well, doesn't that just leave me with, I'm going to try if I can fit this in. Whoops. Let me see if I can scoot this up just a second. So if I do this, I have the distance equals square root of a squared plus b squared. So that's this distance of that diagonal. Now, if I find the distance of the other diagonal, I'm going to change colors. This diagonal right here, and again, apologize for the mess. Let me go way up here. Distance equals the x, difference of the x's, plus the y's, difference of the y's squared. And I'm going to look x's. So I have the square root of 0 minus a. Look at what I had down here. 0 minus a squared. Plus, and then I'm going to do the y's. B minus 0 squared. And I look at that and I'm like, oh, it's a little bit different, but it's okay. Because to be honest, when I square them, it's going to be the same. And when I end up with this, I'll have distance equals square root of a squared plus b squared. Look at those. Look at those. They are exactly the same, even though I didn't use actual coordinates. I used like variable coordinates, and I just used the formulas I have. So trust your math. Trust the concepts to find the length of things. You're going to use the distance formula. Use those coordinates. I know you can do this. You just have to trust the math and the concepts. So prove that the diagonals of a rectangle are congruent. I just did, including a diagram, which I did, which it's kind of messy, but you get it. And then I would just say, since the distances are the same, the diagonals are congruent on a rectangle. Example 3 is one that you want to walk through, and it's a video. And so it says, write a coordinate proof of the concurrency of medians. So first of all, you have to remember what a median is and the word concurrency or concurrent points. Given the triangle with medians AD, BE, and CF, prove that the medians are concurrent, meaning they all meet at one point, the point of concurrency. So you'll click through this video, you'll watch it, and honestly, when you watch this, I'm trying to get to a visual. It goes through it step by step, every single part of the way, and it really helps as you're doing this. Let's see if I can get a little bit better. It helps that you go through this step by step to get the big picture of the whole thing, because this example 3, is going to help you with the next stage right here with the try it. So it walks you through the video, and then you jump here to the try it. It says, to complete this proof of the median theorem, use the distance formula to show that AP, remember AP, that distance is 2/3 of AD. So you're going to actually have to do that math again. You're going to have to show the length of AD times 2/3 is AP. And check that solution once you do that. Example 4, this is how you take these proofs and actually apply them. An interior designer wants the center of a circular fountain to be equidistant from the sides of a triangular lobby. So here's the lobby. Where should he place the center of the fountain? Keep in mind, those things that you learned like way back at the beginning of the year, like angles and things that are equidistant from the sides or equidistant from the vertices, you would have to remember those. But luckily, we just talked about point of concurrency. Hopefully that jogs the memory. But look at these coordinates. Look at these coordinates. So they are provided. Where should he place the center of the fountain? Well, we just did a problem finding the point of concurrency. I think we can do it the same way. So you're going to take these coordinates and try to find the point of concurrency for that fountain to go. This next a table has a top that is a right triangle. So visualize that, a right triangle supports and a single support leg. So it is literally balancing the triangle on one leg. Where should the center of the leg be placed so it corresponds with the center of gravity? Can you remember that vocab way back then when we did center of gravity? So you're like, what are all those points of concurrency? Where either the angles come together, angle bisectors, or the perpendicular bisectors, or the medians. You have to remember which one it is. You might need to look it up. So the points of concurrency of the angle bisectors, perpendicular bisectors, or the medians. There's also one more that we learned, and that was the point of concurrency of the altitudes. Okay, so you might need to look. So this is center of gravity. One of those things was the center of gravity. Plan a coordinate geometry proof to find its location. So again, draw the visual and plan from there. If I had to give you like the big picture of geometric proofs, this is it. So even if, again, this is a really hard lesson and if you get stuck and confused, this is what you need to remember. Determine which numerical relationships you must calculate. So like, are you looking for the length? Are you looking for the slope? Are you looking for like a distance, which is length? Are you looking for an actual point? So mathematically, what would you do if these were numbers? That's the first thing you need to do. The second thing is draw and label an actual visual. So like start at the origin, start to make it as easy as possible. And it even says choose coordinates that simplify computations. Don't just draw a polygon in the middle of a graph. Start at that origin, make your points as easy as possible. And then do the actual calculations. It's okay to have calculations with variables in it. You're going to, especially in this unit, or in this topic, in this lesson. So here's an example. Choose coordinates so parallel lines are horizontal. So like if you want to do anything about parallel, make them always horizontal to make them easy for you. Choose coordinates so the lines of symmetry is the y-axis. So look, here's the y-axis. And if I want them symmetrical, make the line of symmetry the actual axis. Choose coordinates so the coordinates of the midpoints are convenient. So instead of using like fractions, like just say, okay, from here to here is 1. So from here to here, that would be 2. So the total length is 2. So make your coordinates, like plan them wisely. Don't just say A, B, and you have to find the midpoint. That's half, so that would get ugly. So pick your coordinates and name them accordingly. You are choosing the variables, so choose wisely. This, again, is very difficult to understand. The more you practice proofs with coordinate geometry, the better you will become at them. But keep in mind, the more you practice algebraically, like without the proofs, just solving problems like this, like we did in 9.1, the better you will be at proofs. So if you haven't done lesson 9.1, you might want to do that first before jumping into the problems on 9.2. I hope that helps.